Hi, everyone. Welcome to the Introduction to Databases WeCloudOpen class. So tonight we're going to introduce the basic database concepts, and also we will be focusing more on the relational database. So this is part one of the talk series, and in part two, we will introduce NoSQL databases. All right, let's get started. So first of all, I would like to give everyone a quick introduction to the databases. This talk is related to data science, data engineering, and data analytics as well. So anyone who would like to work with databases, I would like to, but this slide is more about data science. I think data science, right? This is the way I look at it. Data and science, and in practice, I think you probably have heard about this. Data scientists will spend a lot more time on data preparation, right, and data understanding, data cleaning, data visualization and exploration, and also feature engineering. The science part is usually deep learning, machine learning, but in terms of the amount of code you write, you're probably going to write more code just preparing data, and even spend more time. So this totally makes sense to me. But some people may think that the science part is the sexy part of data science, right? But now that tools like ChatGPT can, I think conversational AI, generative models, or large language models, it's pretty powerful, right? And the cost of training these models are very high. So I think the new trend in the future is that people are going to be paying for these large models, right? Or doing a lot of fine tuning. So really, I think what makes each organization or company different is just the data they have, they own, and also how they process and prepare the data. So this is the context of this talk, and I would like to help future data scientists and data engineers understand how databases work. First of all, I have a question for everyone. Where does data come from? This is open-ended question. Feel free to unmute yourself and let's have a discussion.
I believe from people for example, let's see, like if, for example, like a person is clicking a lot of like pet pictures, so the algorithm assumes that, oh, that person likes pets.
Yeah,
from that data.
That makes total sense. And actually, we're in this Zoom session. So this session is generating data right now, right? So a lot of these session data we can actually query from the Zoom API as well. For example, who attended the event, right? The Zoom session, how long they stayed in each session. And a lot of metadata about the Zoom session. Any kind of applications, right? Whether it's mobile, web applications, as long as there are people who are using them, it generates data, right? IoT devices, sensor data. So data come from many different places. Anything you would like to add?
I have a question. If data is not captured, is it data?
Sorry, can you repeat the question? If data is not captured?
Is it data?
Oh, yeah. So I wouldn't consider that as data, because usually when we talk about data, we're talking about data in the context of the data that we can collect and that we can analyze, right? So you have to store them somewhere in a computer system. And usually, they're stored in a binary format, right?
Okay.
Yeah. I totally agree. Data is coming from everywhere. So, well, but what types of data?
So the only other question I have, a follow-up to that, is given that it has to be captured and we have to create a format for that capture, then from the very beginning, there's a kind of bias that we introduce into our data.
Yes, I agree. Yeah. So data collection, the data collection process can introduce bias for sure. And that bias may propagate to some of the machine learning models. So the models right? The intelligent models can have biases in prediction as well. So that is actually a pretty big topic in machine learning nowadays, right? So yeah, so that's why I think when data architect or data engineers, design the data collection systems and pipeline, we'll have to take these into consideration because it's garbage in, garbage out. So the more, the better you can, set up the way you collect data, the less biased these systems will be. I totally agree with you on that.
I have a question. So I mean I barely started doing Python like a month ago, and I'm seeing like lists and dictionaries and stuff like that. For like I have for example, like in dictionary, like do you know how there's a key and a value? Would the key be like the value is the data and the key is like cats, for example, or like the input, like someone inputs the data in, will the value of the data, like does it work like that?
Yeah, so it depends on how you look at data, right? So let's say in a database system, the value itself can even be a PDF document, for example, or be a tweet, right? So if you consider tweet as the data, that makes sense. But the key is also part of the data because you can think of it as metadata. For example, who made the tweet? Is it Elon Musk, right, or Donald Trump? So that is data and information itself as well. So everything that we actually store in the database, that the data we capture, we consider them as data. But there's like the raw data, right, that we capture, and there's also processed data. And data engineers and scientists can decide what type of data or what kind of data they would like to filter, right, and work with for their modeling process. Yeah, and you talked about list dictionary. These are Python data types. So they're considered as containers, right, for us to capture data. So I would say key and value, they're part of the data that you deal with.
Okay.
Okay. All right, so let's talk about the types of data, because human generate data, applications generate data. What types of data or what types of data are we, are
就
we dealing with?
是那个是准备那个
Anyone? What kind of data, what types of data are we collecting or are we dealing or are we generating?
Like
So Uzo mentioned audio, video, numbers, text, images. Yes.
Maybe
Numbers.
structured and unstructured.
Bingo. Yes. So we have structured data that we deal with, right? Semi-structured data and unstructured data. So let me try to help you understand these, right? I think all of us have probably worked with, Microsoft Excel or Google Sheet, right? So these are CSV or Excel data. And Excel typically can process like 1 million rows of data, right? When data gets much bigger than that, it starts to get clunky and slow, right? But these are structured data. So basically things that you can put in Excel spreadsheet, right? It has rows and columns or attributes. These are typically considered as structured data. But of course, when data becomes a lot bigger, right? Instead of like 1 million records, now you have maybe 10 million or 100 million records. You probably need to find a better place to store the data because Excel will be quite slow. So we'll talk about the data storage later, but think of the spreadsheet as structured data, right? So for structured data, let's say here we have two Excel spreadsheet or two tables, right? One table has the order related information, so product, right, orders. Another table has the product information itself, right? So the blue table here has product ID, product name, category, and subcategory, and also the price. When data is stored in different places, right? But sometimes if we would like to answer a business question, right, we sort of need to combine or concatenate or merge these data, right? Because the information is coming from different places now. And if this is the type of output on the right-hand side, we would like to merge these two tables to create a new one. How would you do this in Excel spreadsheet? or what Excel function would you work with?
I don't know. I'm not, I don't know if a lot of people use that. I could tell you how to do it in Python.
Yeah, lookup.
Oh, lookup.
Some sort of lookup or joins or merge, right? VLOOKUP, exactly. So we do VLOOKUP in Excel, right? So that means tables can have relationships and you can join and merge them, right, to create new tables. But VLOOKUP can get pretty clunky when you have more and more tables and the relationship among these tables, become more complex, right? And that's why we need to use databases, okay? So database is basically a place for us to store not just the data itself, right? Because these tables, they have rows and columns. So each column will have column name. And maybe you have the data type, timestamp data type, or you have strings, you have numbers. So database is a place for us to not only store the data in these tables, right? But also, those attributes, the schema information, data type, who can access each table, right? Maybe admin can access all the tables, but someone from accounting team can only access accounting or payment related data, right? So rows and permissions, and also the relationship among different tables. For example, this diagram on the right-hand side shows us, how each tables are connected, right? So that's some sort of entity relationship in relational database. So all of these information, which is called metadata, along with the data itself, right, can be stored in databases. And it's just a much more powerful way for us to store data. And then it creates something called SQL, structured query language, so that we can use it to query the data in a much more efficient way, instead of, doing all of these in Excel spreadsheet, right? All right, so we talked about structured data, but we know that there's also semi-structured data. Tweet or Twitter data is a perfect example, right? Someone was asking about Python dictionary that has key value, pairs, right? So the tweet data is actually, you can think of that as like each tweet as, a Python dictionary, right? It has the curly braces and it has the key, which is created. So when this tweet was tweeted and the actual value, right? The timestamp, and it has the ID of that tweet, the actual text. But, tweets can be, images and videos. So sometimes the text key is missing. So it doesn't have this key. So that means this is probably image or video only tweet, right? And it can have some sort of nested structure as well, because when you look at the user is a key, and the data or the value associated with this user key, right? It has a bunch of key value pairs as well. Right, so this is why it's called semi-structured data, because it has the key. Think of the keys as the column names. So you can actually store this in an Excel spreadsheet, right? So created at is one column, ID string is one column. But when you would like to store information about the user in Excel spreadsheet, if user is the column name, it gets a little bit tricky, right? If we would like to store the ID's name, screen name, location as the value in one field in that column, right? So you can still store that as a string, but later on, if you would like to query, for example, I would like to know user ID equals 22449949945. Also, the screen name needs to be Twitter dev. It becomes quite inefficient if we would like to query the data this way, right? So we need to find a better way to store the data, semi-structured data. For example, we can store that in MongoDB, which is a document database. And that allows us to store the data in a more scalable way. But then when we make queries, we would like to extract some tweet and do some search, it's going to be a lot faster, right? So we can change the way we store data in different types of databases, right? There's also the unstructured data.
Sorry to interrupt.
Go ahead.
Sorry to interrupt, but I have a question. How do because we have to do it manually, right? The database, but how do we get data from the other person and implement it into the program? Like it's kind of like what I was thinking was like the input function, and like for example, someone inputs something and then it goes into that value. That's what I was thinking, but
Yeah, I think you raised a good question. So if you're doing everything in Python, then Python has an input method or function, right? That you can just type in the data. But that is not very scalable, right? So we're looking at tweets right now. So there are probably, I think I have a friend working at Twitter. The amount of data they collect in 1 hour is roughly 400 terabyte, right? So that's a huge amount of data. The data will actually need to be ingested into some sort of object store or some kind of very scalable NoSQL databases. And they actually have to compress the data. Otherwise, if you don't compress the data, the data can be 10 times bigger. And that means the cost of storing data will be 10 times bigger. Yeah, so there are different ways for us to input data. You can have in a web application or software, right? Let's say you create a Google form. So the user will be inputting these information, but behind the scene, right, on the server, it collects this kind of data and it will help you store this kind of data in the database. And database is usually the first place, right? The data will go. We'll explain that later, like the entire the workflow. I'll help you understand that. That's one way to to collect data from a user interface, right? But a lot of time data are generated just directly from some sort of IoT device, or even data is read from other source databases and ingest into some other systems. So it can become quite complex. I have a workflow diagram later. Hopefully that'll help you understand this better. Okay. Let's talk about unstructured data now. So, oh, by the way, there are other types of semi-structured data. Every web page we visit, right? That's HTML. So HTML is actually semi-structured data as well, okay? Unstructured data, I think some of you mentioned video, text, audio. These are unstructured data. So this is an image I got from Facebook AI website, right? They have a text to image generative model, which means you just need to type in the text prompt, right? Digital art of a cactus on grass in front of mountains at night, and then it can actually generate images. And of course, it's pretty cool, and behind the scene it's AI models, right? But when you look at the text here and also the generated images here, they are unstructured data, right? So the easiest way to tell the difference here is that unstructured data, you probably wouldn't want to store that in Excel spreadsheet. That's usually how I understand it. As simple as that, right? You can definitely, actually, I was lying. You can store image and semi-structured data in Excel spreadsheet as well, but maybe in a binary format, right? But that means you need to store the entire image, right, in one of the columns. But you can't easily visualize that in Excel spreadsheet, right? Relational database, which you typically deal with structured data, we can actually use it to store unstructured data and semi-structured data, all kinds of data. Now, the challenge with that is when you want to retrieve the data, like when you want to run some queries and about your data and answer some business questions, it's not really built for that, for unstructured data, right? So unstructured data, we need to store them in different format and in different databases. And sometimes it's not even a database. It could be just a data store in Amazon Cloud, for example. Okay, so here's an example of unstructured data. But tonight we're focusing on, in part one of this, this workshop, we're focusing on relational database. Okay, but I'm going to talk a little bit about NoSQL database, which is non-relational database, and hopefully I can help you understand the differences among these different types of databases at a very high level. Okay, what is a database? It is basically an organized way of collecting data, right? So as I said, it not only stores the data itself, but also the data about data. That's the metadata, right? So the schema, tables, queries, and the reports and views and other objects, data about data, different kind of objects, we can store them in a database. don't worry if you don't understand like the schemas and views and stuff. We can share some useful resources with you. So later on when you learn SQL, you know what they mean, right? But tonight, let me help you understand database at a high level, okay? There are different types of databases. There may, oh, sorry, you have a question?
Yeah, so do we get the recording?
Pardon me, I can't hear you very clearly.
Can we get the recording also? Part one, and we can go
Oh, yeah,
over and all
recording
that.
will be available on YouTube later.
Okay, on YouTube later. Thank you so much.
Okay, no problem. There are different types of databases, and mainly they're, the relational database and also non-relational database. So on the top here, we see, the relational database vendors, right? There are open source databases. There's also vendor-owned databases. Oracle, you might have heard of it. It's one of the earliest, databases, and it's a relational database. Very successful company. PostgreSQL and MySQL. They're getting very popular in recent years. And there's DB2, right, by IBM, and also, of course, Microsoft SQL Server. These are relational databases. So why do we have so many different types of databases? First of all, they're created by different companies and they store and index the data in slightly different way. So they're not exactly the same. But the good thing is that the language we use to work with these databases are usually 90% of the time they're just SQL, right? You can have different, flavor, but the way we work with it, writing SQL queries, most of the time it's the same, okay? There's also the non-relational database. And as you can see, non-relational database are typically good for, documents, right? Text data and unstructured data. And there are a ton of, non-relational database technology out there. It's very confusing and sometimes it's, it's overwhelming, right? We'll cover some of these tonight. All right. Just so you know, there has this, huge war between SQL and NoSQL, right? They represent two different worlds. SQL is the query language for relational database. It has been around for so many years, right? And NoSQL came out later. But when NoSQL came out, people say that it's going to replace SQL and SQL is dying. But unfortunately, 15, 20 years later, SQL is still going very strong. I think in the recent years, SQL is having a comeback. And I think one of the reasons is because everyone likes to work with SQL. Developers use SQL, data scientists, engineers, and BI, analysts. We all use SQL, and business analysts work with SQL as well. So it has such a large, user base. It does have some advantages when it comes to building data warehouses and doing analytics. Right? But NoSQL technologies came out of those big tech companies like Google and Amazon, right? So Amazon published a paper called Dynamo, and now it's the DynamoDB. It's massively scalable and globally available distributed database. Right? You can use it to store data at really large scale. So it's much more scalable than a traditional relational database. So it has pros and cons. So when it's scalable, but it needs to sort of, sacrifice some other, important features. We'll talk about the CAP theorem later today, okay? These are some of the database names or vendors you need to know. So I sort of grouped them into the traditional database vendors, right? Oracle, Teradata, SQL Server. These are very expensive database instances or database engines owned by commercial companies and large companies like the banks, right? Investment companies, healthcare. I think these are the companies that use this type of vendor-based database technologies, and they're usually very expensive, but very reliable. Tech companies and startups, they probably couldn't afford Oracle and Teradata when they are just getting started. They're just building their first proof of concept application, and maybe they only have 100 users. It's an overkill to use Teradata and Oracle, right? So they start from open source databases such as MySQL and PostgreSQL, right? And there's also the MariaDB, which is very popular in the past few years. Now there's also a different type of relational database, and these are typically warehouses, right? Data warehouse. Redshift, which is coming from Amazon. There's Google BigQuery and also Snowflake. It's a very successful commercial company. So these SQL databases, they are not open source, right? The one in the middle, in the blue, in the green box, these are open source databases. So typically, a company will need to make a decision what type of database they need to work with, and they may start small by working with, MySQL, for example. But when the application grow, when the business grow, they're going to run into some sort of bottleneck, or maybe they have new use cases, and then company are always going to do migration. They migrate from MySQL, let's say, to a NoSQL database, right? And Facebook did that. They run the largest MySQL database cluster in the world. They still use that, but some of the data is actually stored in NoSQL database, such as HBase or Cassandra. Okay. You're going to hear some terminologies and jargons. There's just so many different things, in the database world. Don't worry if you don't understand all of them. I think if you're just getting started with data analytics, SQL, relational database is all you need. And later on, when you start to work with data engineering, or maybe you want to become a web developer, you may start to work with NoSQL databases. Okay. I'll briefly talk about NoSQL database. This slide may still take me more than 5 minutes, because there are just so many different types of NoSQL database. First of all, it's non-relational database, so it's different from SQL databases. Okay, there's a type of NoSQL database called document database, and typically it has key and value as well. The value part is usually semi-structured, or could even be unstructured text data. Right? MongoDB is very popular, and a very scalable document database. And AWS has its own document database. You can store data in Dynamo as well. And if you work with Microsoft, they have their own document database as well. Okay, I think a lot of the web developers, when they start to learn web development, I think MongoDB is usually one of the tech stack they're going to use, because they're frameworks such as the mean stack or MERN stack. The M is short for MongoDB. Okay, I can only tell you some use cases, because there's not enough time for us to dive deeper into these different types of databases. One example I'd like to give you is location-based search. Right, so this app. I took this screenshot maybe 5-6 years ago. So this is an application called Foursquare. I don't know how many of you still use it, right? But by working with this kind of applications, right, you can use it to search for hot fudge sundae. Right, the search terms are text data. First of all, that's unstructured data, right? And the query is going to be submitted to the MongoDB backend database engine, right? And it's running a query and say, hey, return all the hot fudge sundae related stores or shops nearby. So it's not only doing a full text search, it is also doing the geolocation search, right? And MongoDB is actually really good for that, because when we create, or when the vendor or the store owner, right, go to Foursquare to create their store on Foursquare, they usually need to put in the location information, right, the address. They need to add description, store name, right, the products, the pricing, and all of these data will be stored in the MongoDB as documents, right, and it has key values. Okay, and then when we search for hot fudge sundae, it's going to do the text search, right, but it's also going to do the filter, right, because there might be 1,000 hot fudge sundae stores, but then based on that result, it's going to do the location-based filtering as well. So it's going to calculate like your current location and calculate the distance between your location and other, like those 1,000 stores, and pick the the closest one, right? And this needs to be returned like in a couple of, tens of milliseconds. So, and you need a database that's very powerful and very fast, right? And MongoDB is built for that. What are other things we can use MongoDB for? You can use it to actually store job descriptions. For example, Indeed, I believe they use a different technology called, Elasticsearch or, Solar, but it can potentially store, Yelp data, for example, right? Job description data, and even tweets in MongoDB, and it allows you to search for this kind of, search for tweet based on some kind of text input. Okay. The second type of NoSQL database is the graph database. And graph database is good for storing data that has even more complex relationships. Previously we talked about the VLOOKUP example, right? We have the let's say we have the product information. We also have another table that has the purchase information. So you can do the VLOOKUP, and in Python and SQL, you can do the merge and join, right? To get those information together in the same table. But real life, examples are way more complicated, because you can, there's the, for example, on this graph here, there are people, right? Consider each people as a node in this graph database, and people are connected to each other, right? For example, LinkedIn data is actually perfect for use case for graph database, right? Because on LinkedIn we have people, and people work for companies, right? So imagine you have like so we have people, right? People are connected, okay, but they can be connected for different reasons. So even like, between two people, there might be multiple links, right? Because they are associated with each other. Maybe they are friends, they attended the same school, they work for the same company, or maybe they're in the same, whatever, LinkedIn data analytics user group or something like that, right? Or they applied for the same job, right? So as you can see, in SQL, the relationship is a lot simpler, right? If you want to capture this kind of real life relationships, the way we design the SQL database model, right, is very complex. And for example, in one table, it allows us to only store one type of data. Let's say you have a table about product, you have a table about, the person, right? The graph database allows us to treat every object, right, just as a node on this graph. So you can basically store people, any kind of object, place, company, your resume, right? The type of sports you like, the type of movie you watch. All of these are basically a node on the graph, and then you can create relationship that way. So it's not very structured, right? So that's graph database. And of course, it solves the data storage challenge. But then it also needs to solve, the data retrieval, right, challenge, because we can model the LinkedIn data in a relational database. However, to run SQL queries, to make, to answer some business question, it will take a lot of joins. You might be joining 10 different tables, but in graph database, it's optimized for this type of queries. So the query pattern will be a lot simpler if we would like to work with graph database. Okay. Neo4j is a very successful and popular graph database engine. It's a commercial company, so it's not completely open source. There's another popular one, which is called Tiger Graph. I think ChatGPT recently is very popular, right? And it's not using graph database, of course. It's using deep learning and reinforcement learning. But there are a lot of similar technologies that build something called a knowledge graph, right? Because for ChatGPT to answer this kind of questions, it needs to have context. And a lot of times, company will build a knowledge graph, right, that explains the concept and the relationships between different concepts. And graph database is a perfect fit for that. But I think most of the graph database engine, I think the challenge is still how scalable that is. So there are different ways to tackle this this scalability issue. there's another type of NoSQL database, which is key value store. There are different types of key value store. One example I would like to give you is Redis. This is an in-memory caching database. The best use case is just Twitter. When we use Twitter, it has the home timeline, right? The home timeline information can actually be cached or stored in the Redis, right? So Twitter is using machine learning to generate the home timeline, and they sort the home timeline based on, let's say, time or relevancy and how likely you're going to like these tweets and read them, right? And it's machine learning behind the scene, and they're going to pre-generate this sometimes in real time, but they need to store that in a caching database, and it's Redis. Twitter architecture is actually very complex, and it uses a lot of really cool technology. And Redis is a caching database. It's one type of NoSQL database, and of course, we can use databases such as Cassandra or HBase to store this type of like data, right? But the latency is different. For example, Netflix use Redis. They use Cassandra as well. And a Cassandra database is used to store the recommended movie, right? So those are generated, for example, on an hourly basis. They're going to generate the recommendations to each user. So when you log into Netflix, you'll see the recommended movies, right, in different categories. But let's say that's 5 milliseconds, right? And if you want that to be even faster, let's say sub-millisecond, let's say 1 millisecond, and you have to use Redis, right? Most of the time we don't even notice the difference, right? And most of the applications probably are not at that scale. But when you have hundreds of thousands of people using these applications all at the same time, and you still want every query to return the results in under 5 milliseconds, then you need very powerful databases. And relational databases, where we write SQL queries against, most of the time is not suitable for this type of applications. It's just not as scalable. And there's obviously a trade-off, right? But relational database is really good for business intelligence, data science, whenever we would like to run business queries, right? We're working with a lot of data and doing all kinds of aggregation. That's what it's good for. But if we want to build scalable applications, we need to start working with NoSQL databases. And that's why in a lot of the data science and data analytics curriculum, you won't see NoSQL databases because it's usually not used for that purpose, okay? All right, I'll move a little bit faster. There's also, column family database where, you're building this kind of wide columns, and Cassandra and HBase are two very popular column family NoSQL database. One example I can give you is that you can use Cassandra to model the graph relationship as well. And eBay used to use Cassandra for, whatever, like a product recommendation, for example, okay? Another more relevant database, is actually the search engine database, because everywhere we go, like, Ticketmaster, you're searching for, events, concerts. Indeed, LinkedIn, we're searching for jobs, we're searching for people, right? This depends on the search engine database. And the way they index and store data is, very different and very unique, but it allows you to do search very, very fast. And Google is basically running, right, the largest search engine database in the world. That's the Google search. Of course, they don't use the Elasticsearch, but at its core, they're still using, Lucene, which is how we index the data, okay? That's sort of like the trick and the magic there. It's just like how you store the data, this decides the use cases and how fast you can retrieve the data for different use cases, okay? So just a quick overview of different types of NoSQL databases. There's one thing I would like to mention, which is the CAP theorem. Whenever you start to look into NoSQL database or non-relational database, you'll definitely hear about the CAP theorem, right? CAP is short for consistency, which is the C, and availability, and also partition tolerance. So in a nutshell, when we choose a database engine, like, because whenever you start to build application or do data analytics, you have to decide, okay, so how do we store data, right? First of course, first question is, where does data come from? How do we collect the data? But once you collect the data, you have to make a decision. So how do we store data, right? And what type of databases do we use? When you are at that point, you need to make a decision, right? If we decide to go with a NoSQL database, which is a better use case, like a better fit for our use case, then we have to make a decision, because CAP theorem says that, well, you can't have a database that satisfies all three conditions. So it's very hard to have a database that has the consistency, which is also highly available and is also partition tolerant. And then later on, Google sort of invented something called NewSQL that combines the best of both worlds. It looks like SQL, but it also looks like NoSQL. That's a new technology, which is pretty cool. But CAP theorem is still very relevant, and we don't have time to dive deeper into this today. But I would like to give you just a high level, like, overview of how that works. Okay. But first of all, what is availability? Availability means, let's say, if your database engine, let's say one of the nodes stops working, right? You're still going to get the data you want, but it may not be the most fresh data. And I'll have an example later, okay? Consistency means that when you're, let me show you using this example. It's probably easier that way. Let's take a look at the relational database first, right? So let's say we have a relational database, right? That's storing the YouTube data. Let's say this is, imagine this is just YouTube, right? And we're talking about this particular metric, which is a piece of data we would like to store in the database. How many people have viewed this video? Only 59. So I'd encourage everyone to subscribe to WeCloudData's YouTube channel. So just go to youtube.com/@WeCloudData so we can increase the views. But example here is that if we use a relational database to store this piece of data, like the number of video views, and if we use relational database, which is usually not distributed, right? Which means we store everything in one giant database, right? Very powerful instance. And it's designed to be, or relational database is designed to be highly consistent, which means, we have someone from North America, right? From different countries, okay? Going to this YouTube page. We are all from different locations right now. If you go to YouTube, right, go to the same link, we may not be seeing exactly the same information, the view count, right? Most of the time, majority of the time, it's going to be exactly the same. But relational database, if it's used, it's highly consistent, which means everyone is going to see exactly the same number, 59 in this case, because it's all reading from the same database and it's not really distributed. Okay. However, this is going to cause some problems, right? Because the database server is, in a data center in North America. So that means, people in South America, in Africa, in Asia, when they want to, watch this video, the speed might be slower, right? It's simply because of the distance, and the data packets need to travel longer distance, and that's why it's going to be slower. This actually means that relational database is not as scalable as a distributed system. Right? And of course, there are distributed relational database nowadays, but I'm just explaining the concept here, right? It's designed to be highly consistent, which means everyone is supposed to see exactly the same information. If someone makes an update to this database, right, either everyone is going to see exactly the same. Let's say someone watched the video and the video count should be 60 now, right? And either everyone see this number 60, or somehow there's a problem, then everyone will still see 59. So that's the high consistent system. And it's very useful for for example, the banking and trading applications, when you deposit your money, you want that to be consistent everywhere. You go to online banking, you go to your mobile, banking, and you're at the counter, or at an ATM machine, like whatever channel, you want to see exactly the same balance, right? You don't want that to be inconsistent. So it has a good use case, but it also means that it's not as scalable. And that's why the banks are going to be still, after so many years, banks are still working with IBM database, right? They want to get rid of it, but the risk is just too high. Okay. Now, we talked about the consistency, but let's say if this database somehow is down, it's not working, then nobody's able to access the information. It's going to tell you, sorry, the system is not available right now. That's very typical with, relational database, right? It needs to maintain that consistency. So if the database is down, there's no copy elsewhere, and everyone will stop accessing this until the problem is fixed. So it's less available, right? So which means in the CAP theorem, we have C, A, and P, right? Most of the relational database, right, they are less available, which means they're the AP model. So they're the CP model. They're more consistent, they're partition tolerant, but they may be less available. So for some of the system, it might be okay. But for some other use cases, you probably don't want your user, to be not able to access the information they want. Let's say the Super Bowl happening soon. And you definitely want that to be highly available, because they do that event once a year, right? Okay, now let's take a look at the NoSQL database. And the difference here is that instead of just relying on one database, the NoSQL databases are usually distributed, which means the data can be kept on different servers. They sort of form a cluster, right? In Cassandra, it's called a cluster ring, okay? So these databases are connected through networking, right? And people accessing YouTube in North America, and let's say there are 300 people who just click, let's say during this session, I say, hey, go to WeCloudData YouTube. And then all of a sudden, like in 5 seconds, there are 10 people clicking on it. The view count is supposed to increase, right? So that information is actually written into this database chart here, right? We're talking about very small difference in terms of the latency here, but let's say within a few seconds, right? People in other countries, maybe they haven't seen that change in the database yet, because let's say we have view count plus 5, right? Which is written to this database. It needs to be propagated to the other database, right? Which is the replica. So the database are staying in sync. Okay, so that's how distributed systems work. But the advantage, the clear advantage, is that it's much more available. So in the CAP theorem, the A is its advantage because it's highly available. Because if one server is down, no problem. We still have the data into other replica, right? So the information might be a little bit old, but at least we can still access the data, right? So this part is very different from a relational database, right? And also because we have the database locally, right, or globally in different countries, in different places, the time it takes local people to access the information will be a lot faster, right? Instead of 10 millisecond, maybe it only takes 5 milliseconds. When you have thousands and tens of thousands of people using it, this actually matters, right? So a lot of companies will choose NoSQL database when they consider going global, right? For example, WeCloudData has a learning management system. It's actually quite small right now. We're using PostgreSQL as our production database. But if we start to offer courses, right, in different countries, in different places, right now, everyone's accessing the same database, which is in AWS in the US. You will notice a little bit difference in terms of the speed, right? So I think eventually we'll probably need to switch to a NoSQL database. So it's more available and it's more scalable as well. Okay. So one example here regarding the availability, right? for NoSQL database, you can have 2 nodes stop working, right? But you still have 1 more left, right? So if you have 3 copies, then the chance of losing that database server or losing data is very low, right? So it's highly available. That's one of the advantages of NoSQL database. And there's something called partition tolerance. That's the P in CAP theorem, right? In a nutshell, it means, well, these servers might still be working, but somehow there's like earthquakes and, you know, the cables under the sea is disconnected, and none of these databases can talk to each other, right? But people locally can still access the database, right? So it's still working. They stop syncing data, but the system is still working, right? So that's partition tolerance, okay? All right, so here's one example to help you understand, you know, the consistency, which is the most important concept. For NoSQL database, a lot of them are eventually consistent. So the example here is that we are running a NoSQL database. It has 3 servers, right? They're connected to each other and they'll sync up data, okay? And we have people accessing these videos from different countries, from different places. So this number in the middle, that's 59. Let's say that's the truth. That's how many people actually watched it, right? So right now there's no one watching this video, so the number stays at 59, and all of these databases, you know, are synced up, right? Now, there are people starting to watch the video, right? You have one person clicking on a video, another person in a different country clicking on a video, okay? Just at that exact moment, right? That count is supposed to increment from 59 to 60, right? And from 59 to 60 here as well. But the real count is supposed to be 61 now, right? So these changes, because the data is originally written into these separate databases, and they need to talk to each other to sync the data, right? And then, you know, okay, now we have 61, right? And people accessing this database here, right, just within a couple of milliseconds, if the data is not completely synced up, they may still see 59, right? So this is called an eventual consistent system. And, you know, some NoSQL databases are eventually consistent, which means the number eventually is going to sync up because they will all talk to each other, but the website is still running, right? And you have to pick the right use case for in this case, right? Because does it really matter if someone in India is seeing 59 and someone in, let's say, in Canada is seeing the count of 62? Probably doesn't matter that much, right? So this is a good use case for NoSQL database. But if you're running a financial institution, this is probably something we should avoid, right? So these are called, you know, eventual consistency systems, okay? But eventually it's all going to sync up. All right, so that's NoSQL database. We're still going to focus on relational database today, and I would like to help you understand, you know, how data is stored and how data is retrieved, and then we'll talk about SQL, okay? First of all, use cases of relational database. It's used everywhere. A lot of applications we build internally at WeCloudData, we use PostgreSQL, right? But in large companies, ERP systems, right, that manage data about, let's say, supply chains or employees, productivities, it focuses on, like, you know, reducing the cost, making the company operate more efficiently, for example, right? And these software will use relational databases. Another example is CRM, customer relationship management systems, such as Salesforce, HubSpot, right? Or even marketing applications such as MailChimp, if we would like to do email campaigns, right? They typically manage data using relational database as well. So this is a screenshot of Salesforce, right? And this is the front end. So earlier, someone was asking about like how data is collected, right? We're using this application. Let's say I'm the sales, Jason, right? And I think this is an example from Salesforce, just some sample data. So Salesforce is used to manage sales leads and CRM, right? The communications with the sales leads. Let's say this is a company. And we have information such as the close date, the deal amount, right? The contacts, the tasks. You can create tasks, right? You can add tasks and you'll see them here, and you can log calls, emails. Okay, so where do you think these data come from? Well, they must come from somewhere. It's actually relational databases, right? But it may not come from the same table though. So, you know, the contact information might be coming from like a contact database table somewhere, and there's the deals table, there's the email related table, and sometimes it's a bunch of tables, right? And when we work with this application, right, as a sales, we can add a task, right? And say, oh, I need to follow up with this customer on Friday. And that information is written back to the database. And imagine you're just adding one record to the Excel spreadsheet, right? Or if you're building this in Python, someone was talking about like the input function, similar to that, but you add a UI here, right? So it's much better user experience. But instead of storing this in Python, of course, we're storing that in a database because database is much more powerful and it can store way more data. And if we store the data in Python, it runs only in memory. And if your computer has, let's say 16 gig of memory, you can never store data bigger than that. In memory, I mean, right? In one Python session. So if you would like to store big data and you would like to persist the data, because what if your Python session just died and it lose all the data, right? That's why we need a database. There was a question. Would you be able to explain how is this Salesforce platform connected to the database? This is a concept related to web development, right? So, you know, things like, you know, model version, right? MVC, okay? There's controller as well. And typically we're looking at the UI. So the UI are built using HTML, CSS, and also JavaScript, right? It could be React if it's a web application. So if we click on a button and it pops up, let's say a window, right? That allows us to input data, that's usually JavaScript with some HTML, CSS. But the moment when we put in the data and we hit the send or save button, right? That data is captured by the JavaScript, and the JavaScript will know where to send the data. But where do we send the data to, right? There's something called routing. So your backend system, there's a server that's running somewhere, let's say your Python application, or this could be a, you know, JavaScript application running in the backend. You write the logic, business logic, saying that, hey, if someone click on the add task and save a new task, we need to write this piece of data to certain table in some columns, right? In the backend database. And most likely it's a relational database. That's web application. And your developer will need to like write the business logic. So every button, everything data we input here, right? There's some kind of logic says that, well, this piece of data needs to go into this table in this database. Okay. So let's say this is a CRM system, but when you look at the tables behind the scene, right, it looks pretty daunting because these are the actual tables, but there can be more tables. This might be simplified already. So Fivetrend, this is taken from Fivetrend documentation. This is a company that helps, or they built this Fivetrend product to help company collect and ingest data. What that means is if we, you know, if let's say WeCloudData, if we actually use HubSpot, right? But the example here is Salesforce. If we use Salesforce, and if I actually would like to directly access the data instead of only accessing the data through the UI here, right? Because right now I can look at this company, this lead, right? And I can work with this application to input data and keep track of the deal pipeline in sales. But what if I want to do some analysis and create some report? I would like to know, hey, you know, how's my team doing? You know, as a sales director, I would like to know these information, right? Salesforce provide reporting capability, but companies will always find the need to customize that. That means you want to access the raw data right? And the raw data, as I said, is stored in the relational database. And this is how, you know, Salesforce store their database. Imagine each box here, right, is an actual table. There's a table that stores email messages, right? There's case history. Well, this is related to support. There's also event-related data and sales-related data. So they keep track of, you know, lead, contact, sales marketing campaign, account, opportunity, to track different stages, right? So each one of these are actually a separate table. And the links here just tells us, you know, how these tables are related to each other, so that when we write SQL queries, right, as a data, let's say as a data engineer or data scientist, we need to know how to merge these tables. And this is called entity relationship diagram. That's very useful for you know, for reporting and analytics. Okay, so the data behind these tables, we can actually ingest that into our own data lake and data warehouse, right? So a lot of the data analysts, they're actually going to be working with the data engineers. Data engineers will help the company to, let's say, basically dump the data from Salesforce into their own data warehouse or database system. And then based on the data models, data analysts will be running a lot of SQL queries, right? And then use that to build dashboard and answer business questions. This is another way to look at this. This is more a more generic example. The context here is a bank, right? So we can use relational databases, you know, for ERP, CRM, but working as data analysts and data scientists, most of the time we're actually working directly with the data stored in databases, and we use that for business intelligence, data analytics, and machine learning. But it's important to understand how data actually flows, right? So let's say we have, I think we talked about like the ATM example, right? You just deposit some money. So there's the ATM system, but ATM system is not necessarily owned by the bank itself. Like they're vendors who just specialize in building ATM machines, right? They have their specific technology, and they definitely have a database, you know, that they use. And of course, the banks will need to install those databases to make sure that the ATM machine is talking to their internal database. And those data is usually collected into, let's say, your transactional tables, the CRM systems, right? And there's the credit card data, mortgage data, car loan data, right? Investment data or wealth management, right? Some companies will be dealing with legal documents, which is unstructured. So you probably need to have a process extracting data from PDF documents and then turn that into some sort of structured data, right? And there's the accounting. Oh, it's a typo here, but let's say accounting, finance will have a lot of Excel spreadsheet as well. There are data that's collected directly into the transaction systems or, you know, the CRM system, the ERP system. So these are the data sources, right? But at this layer, that's where the data is originally stored, right? The applications generates data, and the data will be stored in something called like operational databases, okay? But at this layer, we're talking about hundreds, thousands, and even tens of thousands of tables, right? I've worked with, you know, on a project in the past where we had to build a data warehouse for a client, and they have 4,000 tables. And you have to write some sort of script to automate that. There's like, it's going to take you months to look into each and every table. That's why it's very time consuming, right? So this is where actually data engineers are needed, right? Because the data is in a raw format, in the raw systems, but we would like to bring the data into our data warehouse. You know, think of Costco, warehouse, you know, Amazon warehouse somewhere. It's a place for you to stage data, right? And keep things organized. You go to Costco, you always know where to find, you know, different types of products, right? And there's a section for seasonal stuff, right? There's a place for groceries, right? That's a data warehouse, and data warehouse can be used for, you know, by different departments to run business intelligence. But it got to be a process for us to bring the data from different sources, right, into the data warehouse. And that is a process called ETL or ELT, which is short for extract, transform, and load. Right? That's data engineering stuff. So we won't go, deeper into this today. But there are a lot of SQL queries that we need to run, and we need to do automation here. And once the data is put into the data warehouse, which is also relational database, we can logically separate or even physically separate these into smaller databases. And for example, the data warehouse is centralizing all of your data in your company. And you can create a data mart, right? A smaller version of the warehouse just for marketing, because the marketing team probably just need to access the marketing related data. And compliance team, you probably don't want people from accounting and marketing to access the compliance data because it's pretty sensitive, right? So you want to logically separate them. And then data scientists and data analysts will be doing analytics, right? This is machine learning, right? Data scientists will be working on that, but the data analyst and business intelligence, right, specialists will be building dashboards using Power BI and Tableau. Okay, so this is a typical way, for data to flow through the data infrastructure, right? And it can be used for different business use cases. And this, since we talked about the data warehouse, right, we can, in Salesforce, we can generate reports, sales report. But again, these numbers we're looking at right now, they are data, right? Where does the data come from? Well, it comes from the Salesforce warehouse, right? It's a massive warehouse. They have pre-built filters and all the logic. So when you want to create a report, as long as you work with Salesforce, they will create very nice, dashboard for you. But if you want to customize that, then you will have to go through the data collection, data ingestion process yourself to make sure you have access to raw data, and then you have your BI person, doing all of these reporting for you in your own reporting databases, right? Reporting tools such as Power BI. Okay. All right. So now we're talking about accessing the data and using that for analytics and building visualization dashboard, right? So we need to use a tool called SQL. It's a programming language, but you can't really use SQL to build, web applications or build a chatbot. SQL is really only used to query the data or retrieve data from the relational databases. When we work with NoSQL database, we might need to use, programming languages such as Python or Java, JavaScript. But some of the NoSQL database, they also support SQL. So the syntax looks like SQL, but it's also not exactly SQL. It's called CQL, for example. Instead of S, it's called CQL, but it's actually quite similar. Okay, let's talk about SQL. It's a language for us to do a lot of things, to interact with the databases and tables. Right? Now that we have data stored in the database, we would like to retrieve the data. We would like to transform the data. So first of all, you need to create a database, right? You need a database, and you need tables, because you need to tell your developers, your applications, how should we store the data, right? And you design the data models, or the way we structure these tables, also depends on how the data analysts are going to use these tables later, right? So usually we have to, data engineers and data architect will definitely talk to the business and say, hey, how do you want to use these data, right? And because that's important for them to make a decision on the data models and entity relationships, right? And once the tables and databases are created, we can start to store data in the database, right? And then we can analyze the data and retrieve the data for reporting purpose. Why do we need to use SQL? I think it's a no-brainer. Every data job, right, is requiring SQL skills. So it's always among the top 3 most highly in demand skills, right, for data analysts, scientists, and engineers. So if you want to work with data, you'll definitely need to learn SQL. Okay. Different businesses, right? They all use SQL. Tech companies, it's used everywhere. SQL usage across teams, right? Different teams, different organizations in a company. For example, the data engineering team, they'll be using SQL as a language to do ETL, transforming data, extracting the data. And the BI person, they're going to be building the dashboard. The dashboard itself, we're using Tableau and Power BI. But how do we feed data into the visualization dashboarding tool, right? We use SQL. And of course, you can upload a CSV file into Power BI, but that's not how things work in production. Because if you want to upload the data from your laptop to Tableau or Power BI, how do we make sure that the data you're uploading is the most current data, right? Because data will keep changing and you'll keep getting new data. So we better store the data in the database. So everyone, right, who's running the queries, they're all accessing the same table. So the information is more consistent, right? You don't want your data analysts to have their own copy of the table on their laptop, because data will be out of sync and the report will stop making sense. The numbers will not line up, right? Data scientists will be using SQL mainly to retrieve the data and do some data preparation, because the SQL database is definitely going to be more powerful than your laptop. It's going to have more memory, more CPU cores, so it can run queries faster and it can process bigger data set. But data scientists most likely are going to bring that data or prepare data into their Python environment to do machine learning, right? And business analysts, of course, will be doing a lot of the queries and doing visualization as well. All right. This is an extension of what you just saw, like the data flow, right? I won't go through this again, but I just want to let you know how important SQL is, right? First of all, SQL is used to do the ETL, so we can get data into the data warehouse, right? SQL can be used for business intelligence and dashboard. And for companies using big data tools like Apache Spark, they will write Spark SQL. Right? It's not exactly SQL because it's not relational database. Spark is just a data processing engine, but the syntax is pretty much the same as SQL, right? And after the data scientists build machine learning models, they will be doing marketing campaigns. They would like to do A/B testing. They want to do post-campaign data analysis. The data is usually pulled from the SQL database as well. So it's used by data engineers, business analysts, data scientists, and data analysts. And that's why SQL is so important, okay? All right, some examples. You're going to decide which database you would like to work with, whether it's for your company or for learning purpose, right? I think for learning purpose, which engine you use doesn't matter that much. I would recommend MySQL or PostgreSQL. But we choose MySQL for teaching because it has 25% market share and it's open source, right? But the most popular one seems to be Microsoft SQL Server, deployed in many companies because Microsoft has been around for so long, and even Access, right? All right. Now let's talk a little bit more about the databases. When data is stored in database, I said earlier, it's not just the data itself. It's not just the rows and columns, right? We have a bunch of objects, the table. Think of the table as an object, right? A table is just like a sheet in Excel, right? A spreadsheet. And in one Excel file, we can have multiple Excel spreadsheets, right? We can have database views. We can have index, schema. I'll skip some of these because I don't think we have time to cover all of these. But in short, view, right, allows us to limit, right, how we want people to view your table. If your company is working with a consulting company or a consultant, and there's an important table, it has a column called the user SIN number, and or social security number. You don't want people to access that information because they are not internal employees, right? So you can actually use a view to remove that column specifically, and the consultant will only be accessing the view instead of the table, okay? Index is how we optimize the data storage. So when we have data indexed or a table indexed in the database, the way we access the data will be much faster. Right? It's some sort of internal database table optimization. I think for data engineers who are working more closely with database tables or DBAs, they need to understand this concept really well. And sometimes you want index. In some use cases, you don't want that many indices because it may actually slow you down. And a lot of the modern data warehouse technologies like Snowflake, they actually don't even use index. So that's another topic, okay? When you look at a table, right, this looks like a spreadsheet. So there's the column header, right, or just column names. And we have rows and we have columns. Right? I think this is pretty straightforward. But we also have the metadata information or the schema information. Let's say this is the product table, right? There's actually another table that stores information about this product table. Because we have the product ID and the data type is integer. Length is 11, and we have the product name, which is a string. And in SQL, it's called a variable length character, varchar, right? And the maximum character is 200, right? So it looks like you can have longer product names, but we don't need 200 characters for product category, which is usually a lot shorter, right? So this type of information creates constraints, which means you cannot have product name longer than 200, right? That keeps your database like cleaner. This kind of constraints is actually useful, right? And you typically, a relational database running SQL is stricter when it comes to schema compared to a NoSQL database. And the reason why a lot of developers and software engineers like NoSQL database better is because, well, it's more flexible. So they can get started with the NoSQL database to build application a lot faster, because you don't need a database administrator to help you, to sit down with you and discuss every little detail. And we go through 200 columns and decide the length and the data type. None of that. With NoSQL database, it's much more flexible, right? But it comes with a price, of course, because SQL is very consistent, right? And so what is schema? Schema is a collection of these database objects. So it's a collection of databases and tables, right? The data types, and these are typically called schema. And think of it as data about your data, the actual data, right? So that's schema, or sometimes it's metadata. Okay, so we're moving on to index. Index is, I won't spend too much time on this, but it's physical, which means you actually need storage space to store index itself in your database as well, right? And it's a copy of the selected columns of the data, right? You store important information in index, so when you actually start searching for data, running queries, it's much faster. The best example of an index is basically phone book, right? Whatever yellow pages. If you're looking up a company's phone number, right? Or even just on your iPhone, right? In your contact, it's indexed, right? So you can go to, let's say, if you want to look up WeCloudData's address or phone number, of course, you can go to the website, but if you're using yellow pages, then there's this phone book, but you don't, like, it has 1,000 pages. You don't know which page you can find WeCloudData's information. So you have to go to the index, right? Or some sort of table of contents, right? And then you go find the WeCloudData. But still, that's like 20 pages of index information. And you're just looking for WeCloudData in those 20 pages, and it's sorted by the first letter, right? And you just go to W and you find WeCloudData. So that takes you like 30 seconds, right? But then it's going to tell you, okay, WeCloudData is on page 785. You can go that in 5 seconds, right? And on that page, it takes you another 3 seconds to find WeCloudData, right? But imagine without an index, it's going to take so much longer for you to find the information. Right? That's essentially how index work. And of course, there are internal data structure that can make index, run a lot faster. We won't talk about that today. But I'd like to help you understand next how data is actually stored. Okay, before we build the index, we need to understand how data is stored, right? So I'm going to help you understand that through something called HDD, right? It's not the solid state drive, okay, SSD. So it's the traditional HD, hard drive, okay. So it has spinning disks. If you have ever like opened that, it has a lot of spinning disks, right? There's an arm here, right? This arm, it moves up and down, right? And the disk is spinning so that this arm, the tip here, touches different sector, different parts, okay, on this disk. And that's how the computer accesses the information stored on the hard drive, right? Relational databases store data on the hard disk, right? You have to store the data in the database, but the database itself stores the data on the hard drive, of course. It's a computer, right? So imagine you're looking from the top, right? It has something called different tracks, okay? So these are the different tracks, okay? And let's say here we have 5 tracks. And there's also sectors. I'd say in this case, we have 8 sectors and 5 tracks, right? So 5 times 8, we have 40 different small sectors, right? And that is a block, okay? Sorry, we have 8 sectors and we have 40, 5 times 8, 40 blocks, right? And each block, right, allows us to store a certain amount of information. And typically it's 512 bytes, okay? So if we want to access any information on a hard drive, right, we just need to tell the controller that I would like to access the data stored in sector 4 and track 3. And then you will be able to read the data, right? So that means the tip of this arm here will just move to this section and it will be able to start reading the data. Okay, and of course, when we never have to know this underlying details because we just use SQL. But SQL is a query language that will be translated into very low-level language that allows you to access the data that actually is stored on the database hard drive. Okay. All right. So one block is typically 512 bytes, right? Now, let me help you relate this to the actual Excel spreadsheet we talked about earlier, right? So let's say we have 5 rows and 5 columns, right? We have product ID, name, category, subcategory, and product price. You notice that when I talked about the metadata and schema, right? Each column will have a data type. Let's say it's a string, varchar, or it's, numeric or digit, right? Setting the length or how many characters, right, of each column data type matters because each column has certain, like we have to set the data type first. So SQL will know how to store the data and how much does it take, for example, to store 1 record in this table. Okay, we can do the math, right? It's basically 10 byte for each row. It's 10 byte plus 50 plus 25, 25, and 18. We get 128 bytes. Which means one block typically has 512 bytes and divided by 128, that's 4. So that means, each block can be used to store 4 records, right? So this is one block. It can store 4 rows and it can basically store them here. Okay. This is very granular detail. It doesn't really matter. I just want to help you understand what kind of operations we can apply using SQL, and it's related to this. Okay, so let's say in this case, we have 1 block, 4 records. We can store that in 1 block here, right? And when we add 4 more rows, it writes the data to another block, right? so on and so forth. That's how it works. And we can store something called an index as well, right? The index tells us where to actually retrieve the data, right? For example, if we don't have the index, let's say we don't have the index, okay? If we want to access this record here, okay, product ID equals 751, right? And of course, it wouldn't know where to begin with. You know, our database knows that, okay, it looks like our table, you know, it occupies 3 blocks, but in which block can we get that record? It basically needs to read. Sorry about that. Looks like it's a spam. Okay, so let's move on. So back to this topic. If we don't have the index, we will basically have to scan the entire table, which means if we have data stored in 3 blocks, then we will have to read all 3 blocks in order to find that record with the product ID 751, right? But what if we have the index? So index, again, think of it as a table on its own. And the index need to be stored on disk as well, right? But index has a pointer. Instead of storing other information, it will have the product ID, right? But of course, to create an index, we have to decide which column we would like to use to build the index, right? Which typically is the primary key, but you can use other columns as the index as well. And the pointer, it just stores the location information on the hard drive, so it knows where to read that data. Think of it as the block ID. Okay. Okay. So now let me help you understand some of the common database operations, and we'll use the index and table and the blocks to explain that. Right. A typical database operation, there are 4 types of operations. You know, it's called CRUD. So C stands for create. So we can create table and insert data. We can read from this table. We can update, right? We can change the information in a row, and we can even delete a column, delete a row. So we have 4 records in this case, and that takes up 1 block, right? And we have created the index already, okay? Let's insert 1 record. That is basically create, the C here in CRUD, right? When we insert a record, this is how we would like to, you know, appear in this table. But the first thing it needs to do is it needs to actually just write the data on disk, right? Step 2, we're going to actually write that to the disk. But because we have the index, okay, now we need to index this record in the index file itself. So it tells us that if you want to find this record 751, go directly to this block. So you can skip this block, right? So the information retrieval is a lot more efficient, okay? It will be faster. And when we want to read a record, let's say I would like to read, or we basically run a SQL query, right? And there's a where clause saying that I'm only interested in data related to product ID 751, right? And what happens is that it's going to hit the index first, right? And it's basically asking a question, where do you want me to read data from? I would like to retrieve 751. And then based on this, you know, block ID, or, you know, the location on disk, your database engine is going to directly come to this block, right? And it's going to read the entire block. And this block allows you to, you know, store 4 records, and then it's going to find the record that you need, right? Imagine you have billions of records. This is going to become so much more efficient, right? Instead of scanning the entire billing record, you just need to go to 1 block to get the information you need, okay? What about updating, right? So if you want to update a record, you should probably provide the product ID as well, so we can locate, you know, which row it is, right? So again, you're going to read from the index first, go find that record, right? And then let's say we would like to modify the price. It used to be 213, and we would like to update that to 258. It actually needs to update that record in that block. Okay, so that's how update works. And delete, as you can tell, it's pretty straightforward as well. We'll need to delete the data from index. We'll need to delete the data from the actual block as well. So that record will be removed. Okay, so that's CRUD. How some of the commonly used database operations, right? Okay, another concept I would like to talk about is in relational databases, there's a concept called normalization. Normalization means, let's say, when we join these two spreadsheets or these two tables into one table, right? We're actually flattening the data. That is actually called denormalization. Okay, so in something called modern data stack, this is related to data warehouse. So data warehouse is a type of relational database technology as well, right? And companies would prefer to build something called white tables. And it's actually short, the short name is OBT. You can Google it. It's called one big table. So it's interesting concept, but in business intelligence, right? If you want to build a dashboard, data analysts are typically working with a data model, and tables are related to each other. They're connected. To retrieve information, you have to read data from multiple tables. You have to merge these data, and then you can run aggregations and filters and create the table that's used for visualization. And in the modern data stack world, people will say, well, why do you want to do join? Join is always going to slow you down. Why don't we just build one massive, right, big table? And of course, you can find, problems with this approach, of course, but it seems to get more popular. The data will be redundant in some of these, this wide table approach, right? A lot of the information are repeatedly stored, and it takes up more space. So the traditional relational database expert may tell you that, hey, that is a bad practice. But I think, in the modern data stack world, people just believe in this approach. So there are always pros and cons. And yeah, but that's an approach of denormalization. If you're going from many tables to, some big tables, that's denormalization. But if you're going backwards, that means your tables will need to be modeled properly. That's called data modeling, which is something you'll see on this slide. This is related to dimensional modeling, or when companies have a lot of tables in a database, right? They would like to organize the data in a way that you can run queries efficiently, because there are hundreds of users using this database, and there's so many different tables. The way we structure that, ideally, it's going to meet everyone's requirements, because the accounting team want the data to be structured in certain ways, and the marketing team will want their data to be structured in certain ways, right? And sometimes that creates conflicts, that's why we need to do the data modeling upfront, and you need like database architect or people who are very experienced. They're specialized in data modeling, right? And they understand the business requirements really, really well, and then they can decide, okay, let's do it this way. This is how we're going to structure, all the transactional data, the dimensional tables. However, the challenge with that is once you have this data model set, you're going to populate data in these tables in very specific way. Changes will be very hard later on, right? And you start to see some of the limitations of relational database, because on the NoSQL database side, right, we talked briefly about it. People will say, hey, I just want to store the data however I want. It's very flexible. But of course, when it comes to business intelligence, that could be a nightmare, because most of the non-relational database, they don't support joins. They're just not built that way. and join performance is going to be really bad, right? So that's why relational database is still more popular in terms of like business intelligence, because usually we're dealing with a lot of data. Whenever we want to answer business questions, we care less about each individual customer. We care more about how the sales are performing, how's the marketing campaign doing, how's the business doing. So you're talking about this at the aggregate level. So you're always going to aggregate data, right? This is where like things like star schema and white tables will make more sense. And you need someone who's experienced to help you decide this data model, right? And when it comes to data modeling, then there are different approaches as well. Star schema is one of the most popular one, I would say. It's something called dimensional modeling. But basically, you have this really gigantic fact table. This is for sales, right? So you have the actual transactions. It stores like, so basically the fact tables stores the fact. So who purchased what, at what time, in what location, right? At what quantity, at what price point. So these are the fact that happens. That's, you know, the grain of this, you know, or the granularity of this is, you know, the point of sale says that it's usually accurate down to seconds, right? When you made the transaction, made the payment. So this table is usually very big and it keeps growing because people are going to buy more stuff from the company, right? But there are also things that don't change frequently. The number of employees, right? You have a table about employees. The employees, the people who sell the product, who sold the product. And I don't think your products are going to change every single day unless you're doing e-commerce, right? There's a time dimension, right? Year, month, day of the week, or that never changes, right? Your store. So those are called dimensions. So there's the fact and dimension, and they form some sort of star, right, shape, and that is the star schema. And there's also the snowflake schema, which means these little dimensions can actually connect to other tables as well. So it's a more flexible and complex way, but companies will follow different approaches. These are the common ones, like star schema. Okay. All right. This is a very big topic. If you go from database to data warehousing, then you'll have to understand, like, you know, star schema really well and dimensional modeling. Okay. I think we're almost at the end. So I'd like to help you understand how we can also scale relational databases, because earlier I talked about, like, you know, this example of CAP theorem. I said the relational database typically is just one server, right? I was actually lying. You can make it distributed as well, but it still has its limitation. But take this as an example. Let's say, I believe this is, it's Rotten Tomato, right? Movie reviews. There's a concept called database sharding, which means if you use one single database, and it's going to grow in the size is going to grow over time. Let's say we have 3 important tables: users, movies, and ratings, right? But what if your data just keeps growing? Well, one way to solve this challenge is just sharding the data, and you can separate these tables. So you have a database that stores the users, another database storing movies and ratings, right? This can help you solve the immediate challenge if your data is getting too big, right? But the downside of this is, well, if we want to do analysis, we want to join the user table with the movie table and with the ratings table. Now, the tables are not stored, like physically, they are not stored together, which means, right, connecting these databases are the network cables. Like, you sort of need to exchange the data. Like, you have to bring the user table here, the rating table here, so that you can do the expensive join. So for analytics reason, that is actually kind of slow, right? And of course, another way to do this is sharding. And sometimes it's called partitioning, okay? Which means you're going to have multiple database engines, the actual servers, because your data is too big. But can we store the data in a way that we still have all 3 tables in the same database, but we're going to store, let's say, user 1, right? And all the movies this user watched and all the movies this user rated, all, as long as we make sure that the information about one particular user is always stored on the same server. When we do the join can just happen in this server for that user, right? So that is a lot more efficient. So you don't need to exchange the data and send them, to other servers. Okay. So that is called, database partitioning and sharding. And advanced topics, I think most of the time when we write queries, we don't really care about how the data is stored on the, under the hood. But knowing these basics will be helpful. Okay. All right, I think we talked about star schema and snowflake schema already. This is one example of a data model for a bank. Yeah, we're at the end. So introduction to databases, part one. Today we talked about relational database. We talked a little bit about SQL and how data is stored and how data is indexed. And hopefully this this high-level introduction is useful. The recording will be available maybe tomorrow, and I'll send it to Discord, and you can always follow us on YouTube, and you should be able to find those videos.
What's the Discord? Would you like to paste it like in the chat, please?
Oh, sorry. Yeah, I didn't realize that not everyone knows Discord. Let me
Yeah.
send the link.
And if I have a question,
Yep.
so I'm a beginner. Like I barely started getting into Python and like coding and stuff like that. And how could I like start practicing like sorting out files and stuff like that? Like I know like the commands, but I want to like start practicing by myself,
Sorry, can you repeat the question? I missed it.
Oh,
You were talking about files and how do you
no, I was just asking like what's a good way for me to like start practicing on the concept of like receiving data and then like implementing data into it,
So if you're at
SQL and stuff
the
like that.
beginning of your learning journey, my recommendation would be you don't have to worry about the data ingestion part yet. I think if your goal is to become a data scientist or data analyst, then I think you should focus on just imagine the data is stored in the database already, and your goal is still on the analytics side. So you're going to use SQL to retrieve the data and run queries so you can analyze the data. Right? You don't have to worry about how to store the data or how to ingest the data. That's more like data engineering stuff.
Mhm.
And to practice that, I think you need to find some useful like sample data set, and then and just go through a SQL course. By the way, we are open sourcing our Python and SQL course. We call that WeCloudOpen. I think Python is going to be available within the next like in February, and in March we're open sourcing like a SQL course as well. So you can come to our learning portal and you will be able to find all the exercises, recordings, and you can just go through, just learn SQL in a self-paced mode. So we'll make an announcement when they are ready. We're still producing them, but it will be available very soon.
Okay, and for well, right now I'm learning I'm learning Python through
Okay.
YouTube. So
Yeah.
what would you recommend like me searching up like for me to start learning?
I think for Python, there's a really good Udemy course. It's called, I think it's called Python from Zero to Hero, or like Complete Python Guide or something like that. I think that instructor is very famous, but it is a very good course. Yeah, but in the next 2 weeks, stay tuned. WeCloudData's Python course is very good as well. It's something new, and we are making it available to everyone.
Okay.
Yeah, another learning resource is DataCamp. DataCamp has a lot of good resources as well. It's pretty massive. Like there's so many different courses, but sometimes it could be confusing, but you don't need to take that many courses. My recommendation is just like pick one course, go through that. Maybe it's 20 hours video or 5 hours. The practice part is more important. Like just go through different use cases, and you need to start coding
Yeah, because well, right now I found this 12-hour course I'm doing, and I feel like I'm getting the hang of it. I was able to do blackjack by myself, so I feel like that's myself improving, but like I just don't know the concept of it, which I'm trying to learn.
Yeah, so for learning the concept, I think you need to follow a more structured curriculum. That's why I recommend the Udemy course or WeCloudData's open course, because it has slides. The slides, you know, extract like tells you like the most important concept you need to know before you start writing the code. Yeah. Yeah, join Discord. You can ask questions. We're happy to assist you. I've
Yeah,
shared
I
the-
already joined it.
Yeah, okay. There's a question from Christina. How do you collect the data from an app or a form and make sure it lands in the database? Yeah, that how do you make that link? So okay. So the connection between that form, right, and the database, let's say if we, because the web application, whether we're using PHP or we use Python or JavaScript, it's going to read the data from that form, right? Because your front end is going to capture that data, and your programming language like Python, JavaScript, it needs to send the data to the database, and it usually does this through the JDBC ODBC driver, which means any kind of programming language, as long as you have the driver running on that server, it allows you to connect to the database engine, and that database can be on you know in a data center somewhere. It has an IP address, it has the port, and you need to have the right permission. Of course, you need to have the login user, like, you know, username, password, IP address, the port you're connecting to, and the database you're connecting to as well. And you have to tell the database which table you would like to write the data to. So they need to be on the same network. It's reachable, right? And your Python program is going to use the SQL driver to connect to the database and insert the data. So we talked about CRUD today, right? So you can insert the data into a table. It's done that way.
Oh, and I have one more question. When's the next like course or like the next Zoom meeting that we're gonna have? And another question was, I don't know if you guys are based on Los Angeles. I mean, I found you guys through meetups, the meetup app. Are you guys like doing any like in-person meetups or no?
Our meetups are virtual because we don't have a campus in LA. So we
Mhm.
started the meetup, but all of our boot camps and courses are online for US students. Yeah.
Oh, okay.
Yeah.
And
yeah, the courses, the open courses, classes will be going forward. It's going to be every Friday.
oh, okay. Every
Yeah,
Friday,
so
okay.
yeah, so you'll receive either email notification or we'll let you know on Discord. I believe we're going to add the event links on Discord starting next week, so you can always find them. Yeah.
And another question was, oh, okay. What was my question? Oh, and are the courses free of charge? That's my
Yeah, the
question.
Friday courses are free of charge, and as I said, we're open sourcing Python and SQL, and some other courses in the future as well. So those will be free courses, and it's
Oh, okay.
available on the learning portal. Yeah. So there will be an announcement very soon. So. Okay. A follow-up question from Christina. I thought databases are used to store data that is collected from apps, systems, forms. Yes, that's correct. But it seems like it goes the other way too. Data from the databases. Yeah. So the data from the database is usually pulled from your front end, right? Let's say if you want to show a dashboard, right? You saw that Salesforce example, like if you want to see that Salesforce UI like dashboard, then the data is actually retrieved from the database. So again, your application, when you refresh that page and say, hey, tell me the lead status and all the information about this company, right, which is the client, and it's going to actually send a query, right, directly through your PHP, whatever app, to the back end. But instead of inserting or writing the data to the database, it becomes a read operation. So it's going to read the data and pull the data from the database, and then it displays that in the front end, right? Okay. Any other questions?
Oh, I have one more question.
Okay.
I have so many questions, but
No worries.
I have another question. So when a person like inputs their information, so the information goes into SQL or the form, which I'm guessing is a server, like the information is going to go into the server, and then the information from that server is going to go to like a spreadsheet, for example. And from there, Python codes it and separates that information like into different sections. That's what I think is happening. I don't know if I'm right or wrong.
Yeah, let me share my screen. So let's say this is your UI, right? And you have the forms, right? Let's say you have the forms, and you can input data, and there's like a button. You say, hey, let's send this or submit this form, right? In that sends the data. It's captured by your front end. It sends the data to your back end, right? So whether it's PHP, could be JavaScript, could be a Python application, or could be PHP, right? And this, you have your logic here, right? Whatever data you collected, how you want to process them, where do you want to send those data, and that data is written into the backend database. And let's say this is a SQL database, a relational database. In the database, you have the tables, but the linkage here is that you need to have the database driver, right? And then you have the data, right? You're sending the data, you're connected through the driver, and then you're sending the data directly into the database. That's how it works.
Okay.
Right, so data is captured in the front end, right? And it's relayed to the destination through your Python application.
Mhm.
Yeah, and because the Python application will need to know, okay, so for this piece of data, when someone click on this button, you need to send the data to this table, right?
Mhm.
In the database.
Oh, so like I know there's a command like append and stuff like that. Like append update. Like
Yeah, it's basically doing, update, right? Delete, the CRUD
yeah,
update,
like insert, like
and insert.
because yeah. Okay, now I kind of get it.
Yeah. So when you work, when a front end app developer, when they work with the database, it's very different from how a data analyst would work with a database, because the developer are going to mainly work with insert queries, update queries, and delete queries, right? And so the data is stored in the operational or like the production database, but then the data engineer is going to do the ETL, right, to move the data into the data warehouse. This is the data warehouse, right? Because your company will have a lot of databases, and not just one, right? You have a lot of databases and also different types of data, right? And through the ETL process, you're sort of centralizing these data in your data warehouse, and your data analyst is going to write SQL query as well. But the data analyst is accessing all of the data, so he can do, she can do like aggregations and joins and stuff like that. So it's not a typical CRUD operation. They're more likely to work with the entire table. Instead of like the developers is mainly inserting each record or retrieving, several records.
Okay.
Yep.
Mhm.
All right. Another question, is SQL always the language used to do ETL? Not necessarily. If you're building, so if your data is mainly coming from a relational database, I would say yes. SQL is always used, but it also depends on your ETL, like which tool do you use to do ETL? Because if your company use big data tools such as Apache Spark, you can use Spark to retrieve data from different data sources, including the relational database, and then you do all the data transformation in Spark, and then you write it back to your data warehouse. So there are different tools. You can use Spark, you can use SQL. There are also like specialized ETL tools that company use. Some of those are very expensive ones. Thanks, Alan. Yeah, that's how it works. All right. Thanks, everyone. I hope you have a good rest of the day and evening, and I'll see you guys next Friday.
Have a good weekend.
You too. Bye.